Hello, and thank you for joining us tonight. Before I bring on Michelle, please note that I have more programs coming up soon. On Monday, December 1st at 6:30, please join us via Zoom as we learn all about the art of Roy Lichtenstein with our friend of the library, Jeff Measure. Register so that we can send you a URL. On Tuesday, December 9th, please join us as we get a taste of what it was like growing up in the vibrancy of the Chicago South Side in the 60s, 70s, and 80s. As we feature our own Litra as she tells us about South Side, a love letter to my hometown. And that'll be at 7 p.m. in room AB. Rounding out December, please join us as we feature Michelle Gibbons as the ghost of Christmas Past from a Christmas Carol, as she tells us all about the life of Charles Dickens in this living history presentation. That is on Monday, December 15th at 7 p.m. in room AB. Now, please join me in welcoming Michelle Nichols. She's the Director of Public Observing at the Adler Planetarium, and we will discover the latest revelations regarding the planet Venus. Welcome, Michelle.
Thank you so much. And hello, everybody. Hope everyone's staying warm and having a good week so far. So I'm going to talk about Venus, what we know. So far, what we don't know is quite considerable. We actually know more about the planet Pluto. And yes, I did call it planet. I guess we know more about Pluto than we do Venus. It's just not been a target that we've studied extensively. The last time we sent a spacecraft there, last time NASA sent a spacecraft there was the early 90s. So it has been something of a mystery. Now we have learned some in the intervening decades, but there's a lot more that we would like to know. Hopefully, in the next several years or so, we'll send at least one, possibly two spacecraft to go study Venus. So fingers crossed that those actually happen. But I'm going to give you a nice overview of what we know about our closest planetary neighbor in space. So give me just a second. I'm going to share my screen. All right. There we go. All right. And no, you're not missing part of the picture. It really is only a portion of the planet shown here. So the first thing I'm going to talk about is how we even got planets in our solar system in the first place. So planets, solar systems, stars, it all starts off the same way, in a giant cloud of gas and dust in space. And these clouds, we find them all over the place. The one that I'm showing you the picture here is of the what's called the Orion Nebula. That word nebula is Latin. It just means cloud. And so this is a cloudy, fuzzy looking thing in the direction of the constellation Orion. Now, this is a cloud of gas and dust where stars are currently forming, yet to be determined as to whether those stars might eventually, some of those stars might have planets around them. But these clouds of gas and dust are primarily hydrogen. The dust is, think of dust as kind of smoke particle sized rock, metal, that sort of thing. So this dust and this gas starts to collapse, and as the material in the middle keeps collapsing, it gets denser and hotter. And if enough stuff has come together, that stuff starts to make its own energy. And we call that a star. And there is sometimes material left over around these stars, and it forms kind of a flattened disk around the star. And that stuff starts to stick together. Now we have what up on the screen, we have an artist rendition of this, but we get to see these out in space. So these are some of these early solar system type disks that are in the Orion Nebula around a few of the stars. So this isn't just what we think happens, we're seeing this happen. Although this takes a very long time to actually occur. But the material starts to clump together, starts to stick together. And over time, you've got these bits that clump together even more. As these objects get bigger and bigger, maybe they get big enough that gravity pulls them into a round shape. And these are objects that we might call planets. If there are bits that are around the planets, either material that the planet has captured, we might call those asteroids. If they go into orbit around the planet, we call that a moon or a satellite. And so we've got a variety of these types of planet objects in our own solar system, and we know of over 6,000 of these planets around other stars. Now, how the planets turn out depends on a variety of things. It depends on what are they made of? How close or far are they from the star? Are they really hot? Are they cool? Are they really cold? What that temperature helps determine is the type of material that's there. So there's a lot that goes into getting the types of planets that we get. But in our own solar system, we ended up with the planets closest to the sun being the smaller planets, the rocky planets. We call them terrestrial. I'll talk more about that in just a second. But the planets, not only when they form, they not only are orbiting the star, sometimes they get hit by stuff. And so that's what this artist rendition, excuse me, is depicting right here. An early solar system. There's stuff still coming together. Some of these objects are big enough to be round, so we might call them planets. But there's material that is still raining down onto these planets. Now, again, just like I showed you a real picture from the Orion Nebula, how about a real picture from another solar system that looks kind of like this, which is kind of amazing. So this is a very young solar system. And what you've got in the center is where the star is. And then there's material around it. You can see that in rings around the star. And then we've started to see a planet. And it's right here. I think you can see my arrow. So that is that little purple dot. It's not actually purple. They've colored it just so you can actually see it. But it's really amazing to start to actually find these out in space. Again, these aren't just theories; they aren't just guesses. Well, sorry, I'm using that word theory as an everyday version of the word, a guess. In science, we use the word theory in other ways. A theory is actually something backed up by data, and so this is not just a guess as to what these objects might look like in space. In the early stages of a solar system, we're starting to find evidence of that as well. What it could look like from this planet might be something like this. You would have the star really bright in the center, and you got the dust and gas and stuff all around the star that you would see as this glow across the sky. And then you've got the planet embedded in all of that. And you know what? We've seen stuff that looks like this as well. This is an example of a planet that is around a star. So the star is called Beta Pictoris, and the planet is called Beta Pictoris b, and it's embedded in a bunch of this dust. And so this is, again, evidence that we're starting to see what the formation of solar systems is like, which is pretty amazing to see this because we weren't around when our own solar system was formed. So trying to have to work backwards, trying to figure out the steps in the process, the only way we can do that if we weren't around to see it is use the clues of what we got of the planets and other objects that are in our own solar system, but also piece it all together with solar systems that are still in the process of forming. The stars take time to form. Planets take a little bit longer time to form. So once the star forms, that's when you really have the stuff around the star starting to form the planets. Maybe somewhere in the neighborhood of a few tens of millions to maybe 100 million years or so, maybe a little bit more for different types of planets to form. I mentioned we ended up with 4 planets closest to our own sun. Our sun in our solar system is about 5 billion years old. The planets themselves are a little over 4.5 billion years old. So took a little bit of time for all the planets to form. The rocky planets are the ones that are closest to the sun. So what I mean by that is their surfaces are mostly rocky, and they've got thin atmospheres. Again, I'll talk more about that in a second. Um, this could have been what something like an early version of of our own solar system might have been. This is a picture taken at night from a portion of the Earth where it's actually dark enough to see stars. We don't get to see this in the Chicagoland area, but you can see the moon there off in the distance and some bright stars up there in the sky. But what made our own um, planet different from all the rest of them in the solar system, including Venus, as far as we know, is liquid water on the surface of our own planet. That is the one of the main reasons why we're here. We've got life on our planet primarily because we've got a warm enough sun. We're not too close to the sun. We're not too far. And we have liquid water on the surface, plus a variety of other reasons. But Venus is closer to the sun. Venus is going to just naturally be hotter. We'll talk about exactly how hot in just a little bit. But Venus is the object up here in the upper part of the image. Venus is incredibly easy to see. I guarantee you've seen it, even if you didn't know what you were looking at. If you saw something really bright up there in the sky and you went, "What's that?" It's probably Venus. If it was just after sunset or before sunrise, it was probably Venus. Venus is something that basically everybody across the world can see. And it has been something that people have written about for thousands of years. The first known recording of Venus's positions in the sky is this. This is a tablet from Babylon. So it's a Babylonian tablet that is over 3,000 years old. And the writing that you see on this tablet is called cuneiform or cuneiform, where they basically just used a specially shaped stylus, and they pressed these impressions into wet clay, and the different orientations of the stylus meant something. These wet clay tablets were then dried, and so now you had a permanent record of whatever it was that they were trying to record. And a lot of these cuneiform tablets record very mundane things like how much grain was stored in a warehouse, or writing down some sort of transaction between one person and another. But the tablet, this particular one, is recording the positions of Venus in the sky. The ancient Greeks, a little bit later on, initially believed Venus to be 2 separate stars. Phosphorus was the morning star, and Hesperus was the evening star. Later, they realized it was appearances of the same object, sometimes visible in the early evening, sometimes visible in the early morning. This is from a publication called the Dresden Codex. It's Mayan. And the Mayan writing, which became known later as the Dresden Codex, has highly accurate calculations of the appearance of Venus, extremely accurate. And so you can find writings about Venus in the Dresden Codex, and we know that Venus was incredibly important to the Mayans. And so keeping very precise track of where it was in the sky was very important to the Mayan people. Galileo was the first person to publish Venus's phases via a telescope. He may or may not have been the first person to see this, but he was the first person to publish this information. The phases are clearly visible in even a relatively small telescope. And so you can see different images of these different phases of Venus. It looks like phases of the moon. But because Venus goes around the sun, We see the phases. Mercury does too. It's just Venus is a little bit closer to us. It's a bigger planet. We're able to see these phases a little bit more easily through our telescopes. Venus is at new phase when it is between Earth and the sun. And it goes through the other phases, and we use the same words that we do for moon phases, gibbous, waxing, waning, all of that, to refer to these phases. And so what's also really kind of amazing is if you have a good enough image of Venus, you can start to realize when it's nearly in between the Earth and the sun, if you can still see it, you can start to see there's a ring of light around the planet. That's due to its air, and its air is refracting the light through from the sun. So you can actually start to see that Venus itself has an atmosphere, and this is something that we've wanted to learn for a really long time. What was this planet like? Well, one of the first things that became apparent after we started seeing phases, once our telescopes got good enough to be able to check out the planet more fully, we could start to see that it had air. But what was it like? What was it like on this planet? Well, you can start to get a sense of where Venus is in the solar system. Of course, it is going around the sun. So when it's on the far side of the sun, it's going to appear physically smaller in the telescope. When it's closer to us, on more on our side of the sun, it's going to appear bigger. And so ever since we were starting to figure this out, we really wanted to tease out these details. But Venus is really hard to do this with, and I'll explain why in just a second. Maybe some of you in 2004 or 2012, you got to see what was called the transit of Venus. A transit is when an object passes in between, in this case, our sun and Earth. And Venus went directly in between the sun and Earth and appeared as a small disk. And so the transit of Venus, it has been viewed for several hundred years as a way for us to try to learn more about the planet. Between Galileo in the early 1600s and the early 20th century, it was apparent that studying Venus was going to be difficult. It wasn't ever terribly far from the sun. There were no surface features that were visible at all, leading scientists to realize, okay, it had air. We couldn't see anything. It means the surface is completely covered by clouds. We can't see the surface of Venus from Earth. So, well, when you have a dearth of information, then what starts to go into its place? Speculation. So Venus was often portrayed in science fiction stories as lush and green or swampy, and sometimes inhabited by dinosaurs. It In this case, this particular image right here is the cover of a magazine, a science fiction magazine from 1939. And the story of this was the Golden Amazons of Venus. So again, we didn't know an awful lot about it, but we knew it was closer to the sun, completely covered by clouds. It had air. So then all the speculation started coming about, and you got some really fanciful stories. But it wouldn't be until American and Soviet spacecraft explorations of the planet in the 1960s and 1970s that we began to get some very different details. But like I said, even today, we know more about Pluto than we do about Venus. The last US spacecraft was Magellan, and you may have heard of that craft. I'm going to show some images from that spacecraft in just a little bit. But there have been a few more spacecraft since then. The Japanese sent a spacecraft, the European Space Agency did. It just hasn't been a target that people have spent an awful lot of time studying, mainly because Mars took a lot of the focus. Our moon in the 1960s, especially, but Mars later. Places where we thought maybe people could actually go here at some point. Venus kind of got pushed down to the bottom of the priority list. So those terrestrial planets. Venus is just slightly smaller than Earth. Mercury is the smallest of these terrestrial planets. Mars is about half the size of Earth. Um, Venus has about 90% of the Earth's pull of gravity. So the amount of gravity of Venus, the size of it, it's similar to Earth. Honestly, if we were to find a Venus-like planet around another star, and we have, we would call it Earth-like. Earth size is similar, has air, that sort of thing. So is it Earth-like like we would think, temperature-wise? No. But it is something that we do see analogs to Venus around other stars. That word terra in terrestrial, terra means earth. And so these are earth-like, but not necessarily exactly like earth. It really, like I said before, it just means rocky surface, essentially, made of similar stuff as our own planet Earth. But definitely each of these planets has its own characteristics. But the main pieces of information about these that would call these terrestrial are the interiors of these planets. They're generally metallic. The surfaces of these planets, they're generally rocky. The atmospheres of these planets are atmospheres that formed later after the planet itself formed. And the atmospheres themselves are relatively thin. Now, when I tell you a little bit more about the atmosphere of Venus, you go, "Oh, wait a minute. No, that doesn't sound very thin." Compared to the giant planets, Jupiter, Saturn, Uranus, Neptune, yes, these are thin atmospheres. Compared to Earth, Venus's atmosphere is much thicker, but we'll talk more about that. So the interiors of these things, I mentioned they're metallic, but they're not exactly the same. Here on Earth, we have a solid iron core that rotates, and that creates Earth's magnetic field. And Earth has a magnetic field. Mercury has a magnetic field. One of the things that Earth's magnetic field does is it protects us. It provides kind of a barrier of protection from blasts of material from the sun. If you saw the auroras from last week, that's a perfect example. All that solar material that came our direction, most of it was deflected by our Earth's magnetic field. So kind of the magnetic field kind of forms a protective bubble around our planet that stretches out behind our planet as well. And so that's caused by the movement of Earth's core. And so this creates the magnetic field that protects our planet. Now, Venus, no magnetic field. Mars, no magnetic field. It's rather interesting that you've got a planet that's about the same size as Earth, presumably formed in a similar way, and yet the characteristic of this planet for a magnetic field, it doesn't have one. So we'd love to know more about the interior of this planet as time goes on, but we do know that it doesn't have a magnetic field like Earth does. Atmosphere. This is where stuff starts to get really interesting. So we've got 3 of our terrestrial planets have atmospheres. Mercury does not. Venus, you can see evidence of it in the picture. Talk more about it in just a second. Earth, of course, it has an atmosphere. We wouldn't be here without that atmosphere, but it's a relatively thin one. Mars's atmosphere is even thinner than Earth's. But when you take a look at Earth's atmosphere from space, you really get a sense of how thin this air really is. It looks so fragile from space. And so this is looking at a sunset, or I'm not sure if it's sunset or sunrise, but a sun setting or sun rising image of our atmosphere. And just look at how thin, how quickly the image just kind of tails off, and you don't see the thicker atmosphere near the bottom. So definitely something that we're glad we have it, but it looks so fragile from space. But Mars's atmosphere is even thinner than Earth's. Mars's atmosphere has about 1% the air pressure of Earth's atmosphere. So very thin. The equivalent would be if you go up about 20 miles above the surface of the Earth and measure the pressure of the atmosphere there, that's the equivalent of the surface air pressure of Mars. So not no atmosphere, but very little atmosphere there on Mars. Venus, on the other hand, completely cloud covered, high winds up in the upper reaches of the atmosphere that reach 225 miles an hour. So pretty fast winds. Those winds keep the clouds constantly in motion around Venus. And so it takes maybe about 4 days for the planet's clouds to rotate once all the way around. But that's not showing you how quickly it takes the planet itself to rotate. The clouds zip around at about 225 miles an hour. The planet takes about 243 Earth days, the equivalent amount of time of 243 Earth days for Venus to rotate once. So if you look on a calendar and count 243 Earth days from now, look at whatever that date is. That's how long it would take Venus to turn once. So the winds high up where the clouds are, 225 miles an hour. Down where the planet is, the surface of the planet, very little wind, only a few miles an hour at most. This is an enhanced image of the clouds. And so again, we can't see through them. They don't really have a lot of detail. But when we start to look at what's below those clouds, and this is what the Soviet spacecraft did, this is what Magellan helped us do, and I'll have more images from both of those spacecraft in just a sec. But we learned decades ago what the surface temperature of Venus is like. It is hot enough to melt lead. It averages 876 degrees Fahrenheit. The atmospheric pressure, remember, Mars, 1% of Earth. Venus, 92 times the air pressure of Earth. Take the room that you're in and add 92 times more air. It's an incredible, crushing atmosphere. This is the same as the pressure experienced about a half mile down in Earth's oceans. Go to the ocean, go a half mile down. That's the equivalent of the air pressure at the surface of Venus. There's very little variation in the temperature of Venus from the equator to the poles, maybe 5 degrees temperature difference. What's also fascinating is Venus is the second planet from the sun. Yes, it is hotter than Earth. It's even hotter than Mercury, which is closer to the sun. Why? You're looking at the reason why. That atmosphere. That atmosphere holds in the heat like a big giant blanket. Not only that, the atmosphere itself is made mostly about 95% of carbon dioxide. And so that carbon dioxide is very good at trapping heat. It basically takes the heat in and keeps re-radiating it all through the atmosphere. So the amount of atmosphere acting like a big blanket, the carbon dioxide also re-radiating that heat all throughout. There's the clouds are covering the entire surface, holding all that heat in. There's just so much air there. There is a very much runaway greenhouse effect here on Venus, which is actually why we want to study Venus more. Studying Venus's runaway greenhouse effect and the characteristics of Venus's atmosphere might be able to tell us a bit about the physics of Earth's atmosphere and Earth's own greenhouse effect. Now, this is a chart showing the temperatures. That blue line is showing temperature at various levels of the Venus atmosphere. But I'm showing you this to show you what those clouds are made of. I really like this particular graph because it's showing you in very large letters what those clouds are made of. Sulfuric acid. This is an incredibly hostile environment. The composition of the atmosphere itself is toxic. 95-ish% carbon dioxide, a little bit of nitrogen, and some traces of other gases, maybe sulfur dioxide. Nothing we could ever breathe here on Earth. Combined with the density, the pressure of this atmosphere, the temperature, this whole entire atmosphere generates the strongest greenhouse effect of any planet in the entire solar system. So while Mercury is closer to the sun, Venus is by far the hottest planet, especially of all the terrestrial planets. It's probable that Venus has lightning. We don't know for sure. But the sulfuric acid is in the clouds. So people often wonder, oh, could you land some spacecraft on Venus? Well, it has been done. The problem is you have to travel through miles thick sulfuric acid clouds. So that already, before a spacecraft even hits the ground and encounters almost 900 degrees of temperature and 92 times the air pressure of Earth, which melts and crushes a spacecraft, you have to travel through those clouds and even just to get to the surface in the first place. The sulfuric acid also might fall as acid rain, so a form of acid rain. The thing is, you could have these droplets falling from the clouds, but due to the extreme heat at the surface, this sulfuric acid material will evaporate before it actually hits the ground. So no sulfuric acid rain on Venus. Rain would presume that the droplets would all hit the ground, and they don't actually hit the ground. But if we've got these droplets that evaporate and go back up into the upper atmosphere, we have a word for that on Earth. It's called virga. Sometimes we get this here. You might have noticed maybe a meteorologist saying, "Oh yeah, it appears that it's raining below this cloud. We can see this rain on radar, but it's not actually hitting the ground." That might happen when the atmosphere here on Earth is a little bit cooler up above, but the atmosphere down near the surface is a lot warmer, and the rain might evaporate before the droplets hit the ground. So that's what virga is, and that's what we think happens in Venus's atmosphere as well. The clouds themselves are opaque, but they still do let some sunlight through. You just don't see the sun itself. They're too thick for you to see the sun. But the sulfuric acid clouds are opaque. The light can get through. There's kind of a haze below the clouds, but the air right near the surface would be pretty clear. And so this is an artist's rendition of what that might look like. So anyway, it's a really interesting set of circumstances that we've got here, showing these opaque clouds that still can let through some light. Venus is closer to the sun, so the sun would naturally be brighter. So imagine a particularly maybe a bright cloudy day on Earth, and that would be the equivalent of how much light filters through those clouds on Venus. All right, the surfaces, rocky. So how do we see a surface of a planet that clouds cover the entire surface? How do we even do that? Well, this image that I'm showing you of Venus is a Magellan spacecraft image. Magellan had a radar on it, and so that radar system could get radar signals through the clouds, and they would bounce off the surface. And so we know what the surface looks like over the entire surface from these radar signals. And so I'll talk more about that and show you a little bit about how to read some of these radar images that we've got from the Magellan spacecraft. Just to compare some of the other planets, Mercury kind of that brownish gray that you're seeing in this image, that's actual color. This is a true color picture of the surface of Mercury. It looks a lot like our moon, a little bit browner than our mostly dark grayish moon. Our Earth, you definitely know our Earth. Our Earth is covered in blue oceans, white clouds, rocky surface, but with life teeming in all parts of our planet. So our Earth, again, incredibly unique in our solar system for currently having that liquid water on its surface. Notice I said currently. Talk more about that as we go on. Mars. You can see in this picture of Mars, we've got these splotches that are here on the surface. We've got this larger one up kind of at about 10 o'clock on Mars, and we've got these three that are near the middle. Those are volcanoes, extinct as far as we know. We don't think these volcanoes are active, and there are other volcanoes that are on Mars as well. But one of the things that we have seen through many spacecraft explorations of the surface of Mars is very, very good evidence for liquid water that used to exist on the surface of Mars long, long ago. We're talking couple of billion years ago, which was the heyday for Martian rivers and lakes and planet-wide oceans. And so hot springs, freshwater rivers, all sorts of different kinds of water environments on the surface of Mars. The Mars of today is a frozen desert. The Mars of the past definitely shows evidence of liquid water existing on the surface. Why not anymore? Mars has lost its atmosphere to space. Mars has no magnetic field, no protection from those blasts of material from the sun. And so Mars's atmosphere slowly erodes into space. And so we see this happening today. And so as Mars's atmosphere got less and less dense, couldn't hold on to the liquid water on the surface, that water turned from a liquid to a gas, not from heat, from lack of air pressure. And so also we think there could possibly be some of that liquid water under the surface. We don't know for sure. But the question is still out there as to where exactly did all of Mars's liquid water go, because it used to have a lot, still to be determined at some point in the future. So again, we use that radar system to be able to send radio signals down through these clouds to be able to then see the surface. The redder colors in this particular version of a radar image, this is an altitude image. The redder colors indicate higher altitude. The bluer colors indicate lower altitude. What's also really interesting to think about is Venus has in these higher altitude areas, you can kind of think of them kind of like continents, like on the Earth, but you can start to see there's a lot of these cracks and other features that we've got. I'm going to show you better pictures of some of those in just a second, but start to think about these redder areas as higher level continent type areas, and then the bluer areas as those lower lying areas on the surface of the planet. And here we can kind of take a look and see what the whole planet looks like from one side to the next. But here's that Magellan spacecraft radar image. The way you read a radar image in this case, so the last one was altitude. This one is showing you what the surface is like. The way to read a radar image is if you see very bright areas, very light colored areas, those areas are very reflective to radar. They're very rough, very rocky surfaces, boulders, all sorts of rocks and stuff. And then the flat areas, are also reflective, but they're showing you the dark areas are very flat. So the lighter areas, very rough and bumpy. The darker areas on this image, like these splotches over here on the upper left, those are very flat. Very flat parts of the surface. Some of the formations that we see on Venus, and I'm going to show you some of these, and some of them have really wacky names, but some of these we only see on Venus. We haven't spotted some of the landforms that I'm going to show you in subsequent images anywhere else in the solar system. These wrinkled areas, this kind of these bright, kind of streaky looking areas, they're called tesserae. We actually don't know what causes those. And as you can see, they're all over the surface of Venus, but we don't yet know what causes those. So we have a name for them. We just don't know what they are. So yet to be determined on that one. This is a close-up of some of those tesserae. And there's several different ideas for maybe how they form. We need more information and we need better imagery to be able to help narrow down some of the possibilities. But already you kind of look at these and go, wow, that doesn't really look an awful lot like anywhere I've seen on Earth. And you'd be right. These round features, so these round wrinkled areas right here, these are called coronae. Comes from the Latin word corona, which means crown. It is believed that coronae, or coronae would be the plural of corona, but the coronae are formed when hot liquid material underneath pushes upward, and it pushes the crust of Venus into kind of a dome shape, which then collapses in the middle as the molten magma down below cools and leaks out the side. So you've got this molten rock down below, pushes up the surface. That molten rock kind of streams outward through cracks in the rock down below. And then there's nothing else to hold up the crust. And then it kind of collapses down. So think of it kind of like a reverse pancake. So that leaves this round structure. So the area in the middle here is lower than the areas off to the edges. So kind of gives you a three-dimensional sense of an obviously two-dimensional image right here. This is the largest one right here called Artemis Corona. This is about 1,600 miles in diameter. So this is a huge feature on the surface of Venus. And by the way, all those strips are from the Magellan spacecraft. And you kind of get a sense of how it took data. As it orbited Venus, it just took radar strip after radar strip, and it just kept doing strip after strip, kept keeping the radar system going the whole time as it's orbiting the planet. And so you've got all the data in strips. And then what they tried to do was try to overlap each of those strips as much as they could, and then to get a more complete coverage of the surface of the planet. But they weren't able to cover the whole thing. But you can see a sense of how they created some of these images in this particular one. This is called an arachnoid. And what we're looking at is this area in the middle and these cracks over here that kind of look like a spider, hence the word arachnoid. These are only seen on Venus, and they're named for the resemblance to spiders or spider webs. We've seen about 30 of them so far on Venus. And these are these concentric rings and these cracks radiating outward from them. Again, it might be from liquid rock underneath pushing upward, but there's probably more going on here, and we just don't know what the process is. The problem is we don't have an analog on Earth to be able to apply to Venus. So we got to come up with some new ideas to be able to start to answer the question of what makes these on the surface of Venus. This one is called a nova, and plural, novae. A nova is formed when large quantities of liquid rock are extruded onto the surface, and it forms radiating ridges and trenches. And these ridges and trenches are very reflective to radar. And so that's why you see these cracks, these trenches really easily. And there are craters on the surface of Venus. This is a particularly wonderful splat. You can just tell that something from space slammed into the surface of the planet and the material splatted outward. Now, when we start to look across the whole planet, there are almost 1,000 impact craters on Venus. And they're pretty evenly distributed. There's no rhyme or reason. They aren't concentrated in one particular area or another. Craters on Venus range from 2 miles wide to 174 miles wide. There are no craters smaller than 2 miles wide. Why? The atmosphere of Venus breaks apart anything that would normally create a crater less than 2 miles wide. Smaller objects are slowed so much by the atmosphere that they just kind of break apart and then just hit the surface. So anything less than 160 feet wide is just going to break apart. Here on our planet, that might cause a fairly considerable crater, at least definitely big enough to be seen. So you've got these craters that are of a certain size because the atmosphere itself pretty much destroys anything smaller that might make a smaller hole. This crater right here, this large one, is named Cochrane. It's named for famed American female aviator Jacqueline Cochrane. Magellan revealed that about 85% of Venus's craters are pristine. What that means is they formed sometime in the last 700 million years. Think about that for a second, though. Venus has gotten hit by stuff, just like Earth has, all throughout its history. Why are the craters, for the most part, less than 700 million years old? It implies that something resurfaced Venus. Could it have been volcanoes? Maybe a great amount of volcanic activity put magma, lava out onto the surface and smoothed out the surface and did it across most of the surface of the planet. And then stuff after that happened would cause those craters to be formed. Well, exactly what happened is still up for debate. One of the main problems is we don't know for sure if Venus's volcanoes are still active. I'll talk more about that in a second. We think they are, but we don't know for sure. We haven't seen any. None of them have paid us the the compliment of when our spacecraft is staring at the planet to actually erupt at that particular point. We hope we can learn more about that in the future. But these objects right here, these are called pancake domes. These are pancake-shaped domes that may have been lava that was incredibly thick and just kind of came upward and just kind of made a pancake shape and stopped. So we don't see this a lot on our planet, but we definitely see this on Venus. Here's some of these pancake domes, what they might look like from the side. The height has been exaggerated a bit in this particular radar image, but this is again showing you what these pancake shapes look like from the side. So roughly 90% of the surface of Venus appears to be solidified lava. So when you look, this is a real image, by the way. This is an image that was taken by a Soviet spacecraft in, there were several that survived to the surface of Venus, took pictures in the 1970s, 1980s. None of them lasted longer than 2 hours. And so this particular one, these images were all very curved. And there was some work done several years later, several decades later, to kind of flatten them out and so kind of give you a sense of what they look like. The gentleman who did that work, his name there is on the bottom left of this particular image. But here's another one right here. So this is showing you that it looks a lot like Volcano National Park in Hawaii, right? So Venus is covered in a lot of this basalt, and so that would presume it's from volcanoes. Again, we don't know if those volcanoes are active. By the way, just showing you a little quirk of a couple of these Soviet spacecraft. So the way that they worked was they hit the surface of the planet, which bounced the camera cover off the camera. So you can see the camera cover, which is straight on in the middle of the image right here. And this arm right here was spring loaded, and it came down onto the surface so that there could be a contact, put a little science instrument down on the rock so that we could, the Soviets could get data from the surface itself. Well, what's interesting about this one versus this image right here, take a look at where this particular arm came down. That science instrument came down right onto the camera cover. This spacecraft traveled millions and millions and millions of miles only to detect itself with that arm. And there's no way to lift it, move it to another location, or lift it, move the camera cover out of the way. It just happened to be where this particular camera cover ended up, of all the places where it would end up. You know, Murphy's Law strikes even on Venus. So Venus is currently extraordinarily inhospitable, but it may not have always been like that. Several spacecraft have observed rock that looks a lot like granite, and it appears to be granite. Granite on Earth requires liquid water to be able to form. So in the solar system's early days, our sun was cooler. Scientists think that Venus might have had liquid water on the surface for maybe up to 2 billion years. One piece of evidence was provided by this particular spacecraft, Venera 14. So again, this is a Soviet spacecraft. Venera 14 indicated that some of the rocks at the landing site were similar to Earth granite. So there is no water there now. So if it was there, was it really there? For how long? And where did it go? That runaway greenhouse effect provides one clue. Obviously, Venus, if it had liquid water in the past, it got way too hot for liquid water to stay there. But the exact processes that made all of that happen is unknown to us right now. This is a map of all of the volcanoes on Venus. There have been tens of thousands of them identified, and the number could actually be much higher than that. The supply of magma from the interior controls where and how the features, the volcanic features form. The number of volcanoes, the variety of volcanoes, the sizes of the volcanoes, have led researchers to suggest that there's a lot of magma underneath the surface. How is there so much? How did all that accumulate? How does the interior of the planet work? We don't know. This is a giant mystery. So way back at the beginning of my talk, when I talked about the interior of Venus, kind of glossed over it because we don't know much. We know a lot more about Earth. We know a lot more about Mars, and we know a lot more about Mercury than we do about Venus itself, about the interior. This is one of those volcanoes, Ma'at Mons. Venus has 167 large volcanoes that are over 60 miles across. The only type of volcano on Earth that is comparable to that is the Big Island of Hawaii. And the big question is, are any of these volcanoes still active? Yet to be determined. We hope future spacecraft might be able to tell us this, but there is a little piece of evidence that gives us a tantalizing clue. These are two images from Magellan showing a volcano, the same one in each image. Here's one version of it here. This one was a little bit later. Notice that the volcanic vent on one side is different from the different shape on the other side. Does this mean something happened? Did part of the volcanic vent collapse? Did the volcano erupt? Did something happen to change the shape of the vent? Obviously, the shape changed, but what caused that? We don't know, but it's a tantalizing clue that maybe some kind of activity, maybe a volcano, some sort of geologic activity caused this particular vent to change its shape in between the first image being taken and the second. and there were hot spots noticed on the surface of Venus. So everywhere where you see the red indicates where there was a hot spot, and this was the European Venus Express orbiter from about 20 years ago. And so it could create a map of the different relative brightnesses of the portions of the surface. And this particular part of the surface got brighter and then it got dimmer. Was that a volcanic eruption? Maybe, but it's not a conclusive piece of evidence. We really would like to see one of these things erupt directly. How about the rise and fall of sulfur dioxide in the atmosphere? Sulfur dioxide is made by volcanoes. Could a volcano have erupted and put some sulfur dioxide in the atmosphere? Maybe, but without knowing where it came from, it's really hard to say. So there could be at least 4 volcanoes that are active on Venus, but we need more information to be sure. So coming soon, question mark. We hope at some point, couple of spacecraft. One is called Da Vinci. This would be an orbiter and a lander that would go down through the Venus surface and land a craft on the surface. And the amount of time that they would expect the craft on the surface to last would be about 20 minutes. We would be happy with 20 minutes. If it lasted longer than that, great. But it is incredibly hard to cool a computer at almost 900 degrees. You probably know how hard it is to cool maybe the computer that you're watching me on right now. So doing that on Venus is almost impossible. So it's really, really difficult to keep something operating for much longer than that. So we would hope for 20 minutes. Whether or not this mission actually gets launched, yet to be determined. Still on the fence as to whether or not it'll totally get through all the approvals to be able to happen. So, but we hope. And then this one is called Veritas. And it would be another radar system like Magellan, but even better. So the next slide, which I think is my last one. Yeah. Showing you the equivalent of what the resolution was like for Magellan and the equivalent of what it would be like for Veritas. So you can get a really good sense of what we would gain by being able to get more information, get much more detail on the surface if we sent an even more capable radar system. So I just went through all sorts of information that we know and a bunch that we don't know about Venus. I would love to know if you have questions. I'm going to take a quick drink of water right here. If you have questions, if you could throw them in the chat, that would be fantastic. I can't remember. Are they? Let's
Under the
see.
Q&A.
Yeah, or the Q&A. Got it.
I answered the first one, the one from Neil. You've touched on, so.
Got it. All right. So does anybody else have any more questions? Let's see the Q&A. Oh, what is the mechanism by which Venus developed an atmosphere that is so different from Earth? Oh, that is such a great question. We would love to know the answer to that, but there are some things that we can speculate. One of the things that is obvious is that Venus does not have plate tectonics. There's no moving plates like we have here on Earth. And one of the things that plate tectonics is really good at. So you've got all these moving plates. You've got plates that come together and push up mountains. You've got one plate that dives below another and pushes up a portion of that, but you get maybe some earthquakes that form at those boundaries. You've got a variety of things that can happen. But one of the things that plate tectonics is really, really good at is it's part of the carbon cycle. It's how we have carbon in the atmosphere gets recycled into the rocks, stored in all of that, and then gets pumped back out through the into from volcanoes back out into the atmosphere. And so without that cycle, to get carbon out of the atmosphere and there's other ways to do it too, but the plate tectonics, the moving plates, that's a great way of doing it. And without that, you've got carbon dioxide that's released and it doesn't go anywhere. We've got the same thing on Mars. Mars's atmosphere is about 95% carbon dioxide as well. And so there's no plate tectonics on Mars either. So there's no major carbon cycle like we've got here on Earth. So that is one way you would end up with a lot more carbon dioxide in an atmosphere. Now, why there is so much atmosphere, I think the jury's still out on that one. But yeah, this is where when you compare Earth and Venus, you can definitely see a major difference on our planet is the plate tectonics. So, what causes the winds in the upper atmosphere and why isn't it felt nearer the surface? Great question. We would love to know the answer to that as well. That's something that one of the things about the winds not being near the surface, I'm gonna guess a bunch of that is because the planet just rotates so slowly. If you don't have a quicker rotating planet, then the air near the surface is just gonna kind of sit there. But what exactly is driving the winds up high? I'm gonna guess temperature. Is a driving factor of that. It's very hot, but the difference between the upper atmosphere and the lower atmosphere is pretty stark. But we would definitely love more meteorological information about the atmosphere of Venus. That was what the Da Vinci craft would tell us more about as well. So, all right.
Anybody else?
By the way, while you're thinking if there's any more questions, one of the things that they're definitely studying is the high upper atmosphere, the stratosphere of Venus, because that can also tell us about the stratosphere of Earth. Knowing the physics between those two, we can see what's going on in Venus's atmosphere. We can see what's going on in Earth's atmosphere. Again, that's a way to compare the greenhouse effect of one place to the greenhouse effect of another. And so, yeah, it's a really interesting.
I don't
Interesting
want us
way
to
to
turn
study
into
the two. What's that?
I don't want us to turn into Venus. Thank you.
No, we do not.
No,
No, that
no.
yes, that is an excellent point. So, all right, another question. Why does Venus lack plate tectonics while Earth exhibits it? Is a consequence of the difference in mass or proximity to the sun? I don't think so because the mass of Venus is pretty similar to that of Earth. Proximity to the sun probably wouldn't play a part in that because if I mean, too close, too far. You got planets on either side of us that didn't end up with plate tectonics. There's something going on in the interiors or the interior of Venus that is starkly different from Earth. We don't know what it is. And actually, I'm going to a conference in December where one of the main topics that they like to talk about at several of the sessions is Venus and speculation about what the interior is like. So that's another one where you go, hands up, don't know. The why, the how of why one planet ends up with plate tectonics where another one doesn't, where they're of a similar mass, presumably a similar interior, but obviously we rotate a lot faster. We have a rotating core in the middle. What are the layers of the interior of Venus like? Don't really have a lot of information on that just yet. So you're seeing the stark difference in the amount of information that we've got for this planet that's relatively close by versus say Mars, where we've been able to put down basically a Marsquake detector on the surface. So we'd love to be able to do that on Venus, but it would probably only last about 20 minutes if we did. Whereas the one that operated on Mars lasted for over a year, if I remember right. So anyway, the difficulties of trying to study this planet. All right.
Something for the future, for future astronomers
Yes,
and
yes, exactly,
geologists. It's a
exactly.
challenge.
And I would say the Da Vinci craft is, I think that's the one that if either of them happen, it would be Da Vinci, I think, that would get launched first. So, so hopefully I'll be able to learn more about that spacecraft come December when I head to a conference in New Orleans. So, all right. Oh, we've got another one. Oh, the image you showed for a probe includes parachutes. How do you make a parachute that survives hot, high concentration sulfuric acid? You have the parachute not come out in the sulfuric acid, so you can slow. That's the one great thing about slowing a spacecraft down in an atmosphere that is a lot denser than Earth's atmosphere and Mars's atmosphere. On Mars, you need big parachutes. On Venus, you can wait a while to be able to deploy a parachute, because you could just use the shape of the craft itself, its heat shield, to slow it down, because it's gonna slow down in a really dense atmosphere. And then you can deploy the parachute when you're away from the worst of the sulfuric acid. So normally that would be something you need to really worry about, but you can use the density of the atmosphere itself to do a lot of the slowing down of the spacecraft. I must say, Bloomingdale audience has got it going on for questions.
I'm glad to hear that. We've got great patrons, so
you do. That's why I love giving talks to you guys all the time. So this is great fun for me. All right.
Any other questions, anybody?
Last call.
Last call. All right. Michelle will be back in January and February. We will be having two. We're going to have the
armchair tour of the solar system
in January, and then armchair tour of the universe in February. Yes. Now you don't have to. I mean, they're standalone, correct? That you don't have to. You don't absolutely have to. Watch one and
not at all. Nope. Yeah, okay. I hope you do, fabulous. But you do not have to. Not at all.
It's going to be fabulous.
I hope so.
Okay. Well, Michelle, thank you so much. And
you're very welcome.
This has been very. I'm flabbergasted. I just in my lifetime, I've seen so many changes, and it just keeps on coming.
Exactly.
All that money that we give to NASA is money well spent. So
science keeps on trucking. We keep on learning new stuff. And every time you answer one question, you think of 100 more. And
exactly,
and that's the way it works.
But that's the way it should be.
Yep. So, exactly right.
All right. Well, thanks very much, and have a good night,
everybody.
Good night.